Welcome to our Quantum Deep Dive. Today, we are heading right to the very edge of theoretical physics.
I'd say we're going way beyond the edge. We're going to be exploring a concept that could literally rewrite the rules of reality as we know it, the antiqubit.
Yeah, and our guide for this pretty wild journey is a really fascinating theoretical essay by Jörg Oeschneppet. And what he's proposing is, well, it's this incredibly thought-provoking idea that's born from smashing two of the most profound concepts in modern physics right into each other.
Okay, so here's how we're going to tackle this. First, we'll get a handle on the basics, the qubit. Then, we're going to jump over to its mirror image in the world of physics, antimatter. After that, we'll see what happens when you combine them to dream up the antiqubit, explore its absolutely mind-bending implications, face the enormous challenges, and believe me, they are huge. And finally, we'll just kind of ask, so what? What does it all mean?
Exactly. So, before we can even begin to talk about an antiqubit, we really have to get a solid grip on the original, the qubit. This is the tiny engine that gives quantum computing its its unbelievable power.
So, the real magic of a qubit, the thing that makes it so special, is a principle called superposition. Think about it like this. A normal computer bit is basically a light switch. It's either on or it's off, a 1 or a 0. Simple. A qubit, though, that's more like a spinning coin. While it's in the air, before it lands, is it heads or tails? Well, it's kind of both, right? It's a blend of both possibilities at the same time. And that formula you're seeing, that's just the fancy language physicists use to write down that spinning state. Or hey, here's another way to picture it. If that classical bit is your standard on-off switch, then a qubit is like a dimmer switch. It's not just on or off. It can be fully on, fully off, and also exist in every single possible state in between, and all at the same time. And that incredible ability to hold so much more information is the fundamental reason why quantum computers promise to solve problems that are literally impossible for even the most powerful supercomputers we have today. All right, let's just put a pin in that idea of the qubit for a second. We'll come back to it, I promise. Because to build this concept of an anti-qubit, we need to pull in a key ingredient from a totally different area of science, particle physics. Yeah, we need to talk about antimatter.
And look, antimatter isn't just something out of Star Trek. It's real. It was actually predicted way back in 1928 by the brilliant physicist Paul Dirac. He was working on his equations, and he realized they had two solutions. One described the electron, the particle we all know and love, but the other pointed to a particle with the exact same mass, but the complete opposite charge, a positive charge. And the craziest part, when these two meet, poof, they annihilate each other in a burst of pure energy.
So the most famous example of this is the electron's counterpart, which we call the positron. It is absolutely identical to an electron in every single way, except for that positive charge. And this isn't just some abstract theory either. Positrons are used every single day in medical PET scans, so it's real-world tech. In fact, the prevailing theory is that every single fundamental particle has an antimatter twin out there somewhere.
Okay, so how do you actually get from a regular particle to its perfect mirror image? Well, physics has this amazing recipe, you could call it, known as CPT symmetry. It's basically a three-step transformation. First, you flip the charge. Then, you mirror its spatial coordinates, which is called parity. And finally, you reverse the direction of time. The amazing thing is, physicists believe that if you do all three of those things to a system, the laws of physics still work perfectly. And this symmetry, this is the absolute key to our next step.
Okay, so let's put these two big ideas together now. On one hand, we have the qubit, this unit of information that can be in multiple states at once. On the other, we have antimatter, the perfect mirror image of matter. So, this brings us right to the heart of Schnappet's essay, the central question he's asking. What happens if you take the rules of antimatter, that whole CPT transformation we just talked about, and you apply it not to a physical particle, but to a unit of information, like a qubit? What kind of bizarre new object would you even create?
And the theoretical answer to that question is the antiqubit. Now, this is a purely hypothetical object, so let's be clear about that. It's defined as the perfect informational mirror of a qubit. And this is a really important distinction. It's not just a qubit that happens to be made of antimatter. No, it's what you get when you apply that full CPT symmetry, flipping the charge, the parity, and reversing time to the quantum state of the qubit itself.
And when you actually put these two concepts side by side, the differences are, they're profound. For a regular qubit, the mathematical operations that change its state all move forward in time. But for an antiqubit, those operations would be what's called anti-unitary, which implies they run backward in time.
And this, right here, leads to the most radical, most mind-blowing idea of all. A qubit's information flows from the past to the future, as you'd expect. But in antiqubits, its information might flow retrocausally, from the future back into the past.
Right. And that last point Ben just made, that's where things go from being just interesting to being truly, truly mind-bending. Because if antiqubits could ever be made real, they wouldn't just be some little scientific curiosity. Oh no, they would unlock possibilities that sound like they have been ripped straight from the pages of the wildest science fiction.
Okay, so for starters, if you could combine qubits and antiqubits, you could theoretically square your computing power. We're not just talking about an incremental improvement, we're talking about a leap that could be even bigger than the one from classical computers to quantum ones. Imagine creating perfectly unhackable cryptography built on antimatter. Or you could even develop brand new tools to investigate one of the biggest mysteries in all of cosmology. Why is our universe filled with matter and not antimatter?
But let's circle back to the most radical implication here, because it's worth it. Retrocausality. I mean, normally we think of things pretty simply, right? The past causes the present, which causes the future. Cause and effect. But in a system that includes antiqubits, information could, in theory, flow backward. A measurement that you make in the future could actually influence the state of a particle right now. Just think about that. It completely flips our entire understanding of cause and effect completely on its head.
Okay, this all sounds absolutely incredible, I know. But before we get too carried away planning our time-traveling computers, we need to pump the brakes, hard. It's time for a major reality check. Because the leap from a beautiful, elegant mathematical theory to an actual physical reality is, well, in this case, it's monumental. The practical and experimental hurdles are almost unimaginable.
And just to put this challenge into perspective, look, building a stable quantum computer is already one of the hardest engineering problems humanity has ever tackled. Qubits are unbelievably fragile and sensitive, but the difficulty of just isolating and controlling a single qubit? That's absolute child's play compared to the monumental, almost impossible challenge of trying to isolate an antiqubit.
And here are the reasons why. First, and this is the big one, annihilation. Since an antiqubit would have to be based on antimatter, the instant it touches even a single stray atom of regular matter, it's gone, instantly. Second, the antimatter systems we can create, like positronium, are wildly unstable. They decay in tiny fractions of a second. Third, just containing the stuff requires immense energy, ridiculously powerful magnetic fields, and vacuums better than deep space. And maybe the biggest roadblock of all, we have absolutely zero experimental data to suggest we can even create a coherent quantum state in antimatter, let alone control it like a qubit.
So, you might be asking yourself, if these things are practically impossible to build right now, then what's the point of even talking about them? And that's a fair question. The true value of the antiqubit concept, at least for now, isn't as a blueprint for some device we're going to build next year. Its real power is as a tool for thought. It's a concept that pushes the absolute boundaries of our imagination and forces us to question some of our deepest, most fundamental assumptions about how the universe actually works.
Yeah, and this idea really gets to the heart of Schneppet's essay. The antiqubit isn't just about building a faster computer. It's a philosophical promise. It's this hint that our entire understanding of information, of reality, of time itself, might just be one side of a much bigger, much more beautiful, and perfectly symmetric coin.
And that leaves us with a really profound thought to end on, doesn't it? We all instinctively feel that our present is shaped only by the past. It's just common sense. But what if the universe is more symmetric than we think? What if concepts like the antiqubit are pointing to a deeper truth? Could it be that our reality isn't just a product of the past, but is actually a kind of conversation? A dialogue between what has already happened and what is still yet to come?
And that's a question we'll have to leave you with. This whole deep dive was, of course, based on the fascinating theoretical work of Jörg Ove Schneppert. So if your curiosity has been sparked and you want to explore more, we highly recommend you visit his website.
Thank you so much for joining us on this journey to the very edge of information theory.
Goodbye for now.
Schneppert.de is a private project by Jörg Ove Schneppert dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.